Hello again. Last time I talked about graph transformations, covering pretty much the material in the A-level syllabus. This time I'm going to take those same ideas and stretch them much further, beyond, well, probably beyond what's sensible actually, but it's good fun. So the last video might have been useful for your teaching of this topic. This one certainly won't be, it's just for your own amusement. And it is rather fun. So let's get going. So last time I finished with a slide that started by reminding us that the graph is to be thought of as a set of points, x, f of x. And we concluded that to transform the graph of f into the graph of gf, where g is another function, we apply the function g to the y-coordinates of those points. To transform the graph of f into the graph of fg, we apply the mapping inverse of g to the x-coordinates of the points. Now, if you're not comfortable with that last bullet, then you perhaps might want to watch the first video. I also said that this works for any old g, although we only use very simple g's in the last video. So I want to start by demonstrating that in a couple of ways. So we're going to create the graph of sine of x squared over 4 using nth in two different ways. And the first is as a transformation of the graph of y equals x squared over 4. So the rules for these nths are they start on the x-coordinate, on the x-axis, and they have to move to the new graph to the point x sine of x squared over 4. They don't know the formula for the graph they're given, but they do know the formula for everything else, and they can do all the calculations. So in order to go to sine x squared over 4, they first of all have to find f of x. So now they've got x squared over 4 as their y-coordinate, and then they take the sine of it. Okay, so that's fairly straightforward. Now the other way around, this time we've given the ants the graph of the sine function, but they don't know that it's a sine function, they just know it's a curve. So in order, and they've got to, again, go to the same place. So in order to find out what sine of x squared over 4 is, the only option they've got is to go to x squared over 4, and they've done that there, and now there are two ants in each of these places, and find the value of f. And then go home, because now they've got their y-coordinates correct, but they're not at the correct x-coordinates, so back they go, taking the graph with them. So let's look at that last bit again and see what's going on. Focus on this point here, for example, where there are two ants that arrived with an x-coordinate of 1 because their original coordinate was plus or minus 2. So to go back, they're going to go back to plus or minus 2, and so the transformation that's applied is to go from x to plus or minus twice the square root of x. Okay, so these are the same bullets we've already had. What I didn't mention last time is to transform the graph of f into the graph of hfg. So g is now a function applied to the input and h is a function applied to the output. We apply the mapping inverse of g to the x-coordinates of the points and apply the function h to the y-coordinates. So let's get the ants to do that as well with mod sine of x squared over 4. They've got to create the graph of mod sine of x squared over 4. So they go to x squared over 4. They find the value of f. And then they go home. And then all they have to do now is take the modulus of their y value. That's the easy bit. There we go. Let's look at the function machine version of this. So f is our starting function. We're applying g to the input and h to the output to create the new function hfg. The graph of f consists of points x, y, where the x comes from here and the y comes from here. The graph of hfg consists of points x, y, where the x comes from here and the y comes from here. So to transform this graph into that graph, we take all these points x, y, and take the x backwards through g and the y forwards through h. And of course, if there's more than one value here that arrives in the same place here, we need both of them on the way back, as the ants have just demonstrated. The other thing that we introduced last time was that the mappings have graphs as well. It's just that some x values have more than one y value. And these graphs can be transformed in exactly the same way. So let's look at this circle. This is the unit circle. We normally think of this as the equation of the unit circle, which is just Pythagoras' theorem, isn't it? If we rearrange it like this, then this piece here is a mapping. For x's in the domain, most of them produce two outputs. So now the unit circle is the graph of this mapping. And if we want to transform that graph by moving it left 2 and down 1, well, we know how to do that. To move it left 2, you add 2 to the input. And to move it down 1, you subtract 1 from the output. And then if you rearrange those back the way they came, you get the equation you knew you were going to get, which is that. So it really does look as though it's going to work here. One more example with ellipses. So this time we're starting again with the equation. We turn the circle into the graph of a mapping. And now we want to shrink this in the x direction by a factor of √3, stretch it in the y direction by a factor of √2. Well, again, we know how to do that, don't we? So to shrink it in the x direction, we multiply the input by √3. To stretch it in the y direction, we multiply the output by √2. And again, if you rearrange all that, you get that, which you knew all along was the equation of that ellipse. So the conclusion is that the graph of a mapping consists of points x, y, where y is any of the outputs of f at x. To transform the graph of a mapping f into the graph of gf, apply the function g to the y coordinates of those points. To transform the graph of f into the graph of fg, apply the mapping inverse of g to the x coordinates of those points. And you can do both. To transform the graph of f into the graph of hfg, apply the mapping inverse of g to the x coordinates and apply the function h to the y coordinates. Okay, so there's another way to think about the unit circle, which is to start expressing the circle this way. And then it looks like an example of an implicitly specified curve, in which you do by with a 2-input function, and the curve consists of those points x, y, for which f of xy equals 0. These curves can be transformed in just the same way. So let's go with the circle again. So this time it's an implicitly defined curve, x squared plus y squared minus 1 equals 0. Well, we know what this one is, don't we? It's x plus 2 squared plus y plus 1 squared minus 1 equals 0. So it really looks as though in order to move left 2, you add 2 to the x input. In order to move down 1, you add 1 to the y input. So x and y are both inputs to this function, and so in both cases, the transformation of the circle is the inverse of the transformation in this algebra. So let's look at the function machine view of that. Here's a 2-input function machine, and we're only interested in inputs for which the output is 0. So we're going to apply g to that input and h to that input to create our new function. So now the graph of f of xy consists of points xy where the x comes from here and the y comes from here. The graph of f of g of x, h of x consists of points where x comes from here and y comes from here. So to transform this graph into that graph, we take all these points and move the x's backwards through g and the y's backwards through h. Okay, so let's get the ants to do that. We'll get them to start them by moving the circle. So this time we need a new sort of ant. We need an ant at every point on the plane. And their job is to light up bright red if they're on the transformed curve and to fade away if they're not. And as usual, the rule is they don't know the equation for this thing. But we do, though. The equation is that of the unit circle. And the functions we're applying to the input, g of x is x plus 2, and h of y is y plus 1. So the first thing the ants have to do in order to find out whether f of g of x, h of x is 0 is to go to g of x, h of y. So there you go. They go right 2 and up 1. Then they discover whether they're on the curve or not. And those ones discover that they are. And then they go home. So let's look at that again. So these particular ants, right from the beginning, went right 2 and up 1, found they were on the curve, and then undid that transformation. So it looks like, as again, the transformation that applies to the curve is the inverse of the transformation in the algebra. Well, that's a very simple function. These are both one-to-one functions with inverses of functions. So for my last example, I'll give you one that isn't. So this time, we're going to transform the straight line into a circle. So our starting function f defines this simple straight line, f of x plus y minus 1 equals 0. The functions we're applying to the inputs are in both cases to square them. In other words, f of g of x, h of y is x squared plus y squared minus 1. And that's 0 on the unit circle. So let's get the ants to do that. So first of all, they don't know the equation for the line, so the first thing they have to do is go to the point g of x h of y to discover if they're on the curve when they get there. So there we go. Now that's quite... So they've squared both their x and y coordinates. So there are 4 ants in each of these places. And then they have to discover whether they're on the curve or not. And these ones discover that they are. Now I've just made one of those blues so that you can see a little bit more clearly what goes on. So there are now 4 ants in each of these places, and they now have to go home. So watch this, it's beautiful. There we are. Created the unit circle out of a straight line. Now let's watch that again. So each of these 4 ants, let's take the blue ones, they have come from the 4 different quadrants by squaring their coordinates. So to go back, the point, if the coordinates of this point are now x, y, it has to go to plus or minus the square root of x plus or minus the square root of y. And that's what they do. There we go. Isn't that wonderful? To summarise that, the curve defined implicitly by a 2-input function consists of those points x, y for which f of xy is 0. And to transform the graph, transform the curve defined implicitly by this equation into this one, with g of x and h of y applied to the inputs, we apply the mapping inverse of g to the x coordinates and apply the mapping inverse of h to the y coordinates. Well, that was quite a ride, wasn't it? So next time I'm going to come right back down to earth and cover a topic slap in the middle of the A-level syllabus that I love to teach because of the connections it makes elsewhere. And that's one-dimensional vectors.